Hello and welcome back. In this slice of physics, we're going to talk about apparent forces in circular motion. We're going to take the example of a person on a roller coaster going on a vertical loop and see how heavy or light the person would feel at the very bottom and at the very top of the loop. And we'll also touch upon the disoriented feeling we get in roller coasters because our body is confused as to which way is up. Here's the question that'll help us cover all that. It says that a 60-kilogram person rides a vertical loop in a roller coaster in which the cars remain on the inside of the loop during the vertical circle. The radius of the loop is 6 meters and the cars move at a constant speed of 8 meters per second. What is the person's apparent weight at the bottom of the loop and at the top? How do these compare to her weight? And I've already put the solution steps in here because we always follow those. So let's do a picture. So here's the roller coaster going in a perfect circle vertically and then continuing on. So the cars are going this way. The radius of this is given to us. I'm going to write it as r here, and r is given to us as 6 meters. And the speed with which the cars are going, v, is given to us as 8 meters per second. And what we're asked for is what is the apparent weight over here and what is the apparent weight over here. The car remains on the inside of the loop and the person is sitting on their seat. Okay, so the next step was to draw the free body diagram. So let's do that for the top and the bottom. So I'm going to start at the top, and this is the person that we're interested in. So at the very top, the person is upside down with the seat above them. So here's the seat, here's the person sitting upside down like that. And they may be wearing a safety seat belt, but we really don't need that if the cars maintain the speed. So we are not going to worry about any forces from the seat belt. They are just there for safety in case the cars stop, which is not happening in our example. So as I go around the person, the only contact is with the seat. That'll give a normal force, and normal force comes out of the surface and perpendicular to the surface. So here's the first weird thing with this. The normal force actually points down. We're not used to it pointing down, but there's nothing that says that it can't. Remember some of our earlier examples, the normal force was actually horizontal when you were leaning into a vertical wall. So the only thing we know about the normal force is that it's always perpendicular to the surface and comes out of the surface. So it's got to point down in this case. Then I've got the weight of the person that always points down, which is the long range force, and those are the only two forces I have. So clearly this person is not in equilibrium. And that's fine because they are going in a vertical circle, so there is a centripetal acceleration that points towards the center, and there's a centripetal force that's connected to that centripetal acceleration. So we know that for this diagram there is an acceleration that is v squared over r that points in the downward direction. Okay, I've got my free body diagram, my axis, so I've got y pointing like this, and I'll also show x even though we don't need it. So now I can set up my equation. I don't need step 4, both forces are along y-axis, so I can go and set up the equation for the y-axis, which says that sum of forces in the y direction has to be equal to m times ay. So when I put in the forces, I've got minus n, because it acts downward, the y-axis is positive upward, minus w, that's also acting down, equals mass times the acceleration is also negative, so I'll put a minus over here and write ay. And as we said, ay is v squared over r because it is centripetal acceleration. Anytime you have a circular motion, the acceleration is given as v squared over r, pointing toward the center. So all the minus signs go away, and I can simplify this as n plus w equals mv squared over r. And w is simply mg, so I can write this as normal force equals mv squared over r minus mg. So what we have done so far is what I would call the physics part of the problem, and that's the important part, to understand the question, set it up correctly, and set up the equations. The last steps from here on out are just simple calculations. And I'd like for you guys to focus on this physics part of solving the problem as you work through these questions. Now it's just mechanically putting the values in. So I've got 60 times 8 squared over 6 minus 60 times 9.80. And when I solve for that, I will get an answer of 52 Newton. And because we are used to talking about weight in pounds, I'm going to give you the pound value of that. That is 11.7 pounds when I use the conversion factor that there are 4.45 newtons per every pound. And if you remember from a previous video, normal force is the apparent weight, which is why I went down this path to figure out the normal force, because we are being asked for what is the person's apparent weight. And it's also asking us to compare it to her actual weight. So her actual weight was just mg, which is m times g would be 60 times 9.80, which gives me 588 Newton or 132 pounds. So the person's actual weight is 132 pounds, but at the very top of the roller coaster, the person feels a lot lighter, only 12 pounds roughly. Let's see what happens at the bottom. So at the bottom, the seat is over here. The person is sitting on the seat like this. And so as I go around the person, I've got a more normal situation here. So my normal force would point upward, perpendicular to the surface, and that's the only contact force. So my free body diagram would look like this. I got normal force pointing up, and I've got the long range force of weight pointing down. And now my acceleration in this case still points towards the center. It's still a circular motion, but now the center is towards the top. So the acceleration A is going to be v squared over r towards the top when I'm at the bottom. So now when I set up sum of Fy equals m times Ay, I would get plus n minus mg equals plus mv squared over r. And so I can solve for n as mv squared over r plus mg. And now when I put all of the values in, it'll be 60 times 8 squared over 6 plus 60 times 9.80. And that'll give me 1230 Newton. And in our familiar terms, we'll convert it to pounds by dividing by 4.45. And that gives me 276 pounds. So this person who has an actual weight of 132 pounds feels a lot heavier when they are at the bottom, more than twice their weight, and feels a lot lighter when they're at the top. Now these sensations are probably consistent with what you feel as you ride a roller coaster. But it really depends on the speed. If I had these cars moving at a lot faster speed than 8 meters per second, even when you're at the top, you could feel something that's comparable to your weight or even more. But the apparent weight at the top would always be less than the apparent weight at the bottom. Okay, one final point I want to make here. I mentioned that if the car stops, bad things happen. You start falling, the car starts falling. And we don't want that to happen, which is why we have safety harnesses, etc. But there is a minimum speed that'll keep you pushed into your seat. And you can figure out what that would be. Basically, as you slow down, you can look at these equations and figure out that as you slow down, this v squared goes lower and lower and lower, which means this mv squared minus mg gets to be a smaller and smaller and smaller number. Eventually, you will get to a point where this n would simply become 0. So if the normal force becomes 0, the seat's not pushing down on you, which means you're not pushing up on the seat. Remember Newton's third law. And so you would fall down. So that's why roller coasters have to move at a minimum speed. And then the other thing is we talked about which way is up. So normally when you're standing on the ground, your normal force is up, but you feel your weight being down. The apparent weight that you feel is the third law pair of the normal force. So it's always equal in magnitude, but opposite in direction. And because of that, when you're at the bottom, even though you feel heavy, it's okay, you're comfortable with it because normal force points up, your apparent weight points down, which is what you're used to. But when you're at the very top, your normal force actually points down, which means your apparent weight points up into the sky. And so the fluids in your inner ear tell you that down is up, and your eyes tell you the opposite, which is what creates confusion and the feeling of nausea. And closing our eyes doesn't really help either, because we're not used to the direction of up changing so rapidly, especially when our eyes are closed.